Hi guys, Patrick here from EngineeringShock.com and ElectronicLessons.com. I'm going to do a tutorial today. I'm actually going to break it down into 3 parts. I'm going to show you how to make a little laser detection circuit. It's very simple. I've seen a few other tutorials online, but they don't really get into exactly in detail how it works. So, in essence, I'm actually going to design it in front of you, and I'm going to build it on this breadboard, and you're going to follow along. So first of all, let's build our little power supply. We're going to need 5 volts. So first of all, if you're going to use a 9-volt battery, let's say you're using a 9-volt battery. You've got 9 volts, your positive 9 volts, and your negative 9 volts. 9 volts ground, and ground DC. And that's connected to pin 2 of 7805. Left pin is 1, right pin is 3, middle pin is 2. 1, 2, 3. So we want to place our 9 volts, our positive 9 volts DC on pin 1, ground on pin 2, and our third pin will be outputting a regulated 5 volts. And we've got 2 capacitors here between the output pin 3 and ground, which is also connected to pin 2. You've got a 0.1 microfarad electrolytic, 2 leads of the same length. They are it's not polarized, and 10 microfarad electrolytic. 1 lead is long, 1 lead is short. Long lead is positive, short lead is negative, in which case we're going to connect to ground. So you'll notice that we've got a little triangle symbol here. That means that anything with that indicator will be connected to our DC ground. We've also got a 5-volt indicator, meaning that anything with this symbol with plus 5 volts will be connected to the 5-volt line. So first of all, place your 7805, which you can find all of these components that I'm about to show you at Radio Shack, in the left side of the board. Take a black wire, place it in your ground rail. I don't have many red wires, so I'm just going to use an orange one for pin 1, which will be where I put my plus 9 volts. I'm going to take just a generic wire from my ground line, and I'm going to put it into pin 2, grounding it. Just going to bring this a few dots back. There we go. So now we've done everything but the regulation side. So what we can do is take our 0.1 microfarad ceramic capacitor, place 1 lead at pin 3 and 1 lead at pin 2, because the secondary lead is connected to ground, and so is pin 2. So pin 3 to pin 2, easy connection. And as well, so now we want to take our 10 microfarad positive lead on pin 3, short lead on pin 2. Lastly, what we want to do is we want to take one more red or orange wire, place it in pin 3, and put it in our positive rail, which is on the top here. So now we have regulated 5 volts and access to ground on the tops and bottoms of this breadboard. So now what we're going to have to do is we're actually going to have to worry about the LDR circuit, the laser detection circuit. So let's talk about that now. Now we have to make our laser detection circuit, obviously. Now we're going to do this step by step so that you understand exactly what's going on. I've got a 10K fixed resistor connected to the 5-volt line, and an LDR, light dependent resistor, connected between the 10K resistor and ground. So what we've got is a voltage divider here. If we had 10K here and 10K here, we'd have 2.5 volts in the middle. It's a ratio. So it's essentially 5 volts divided by our total, which is 20K. 10K plus 10K is 20K, multiplied by 10K, which is this resistor. We would have 2.5 volts there. So really, the LDR is it's a variable resistor. In light, this specific LDR that I'm using offers about 1 kiloohms of resistance, and in complete darkness about 100 kiloohms of resistance. So if we run an example, again, 5 volts divided by our total, which would be, in the case of light, 11K. In the instance of darkness, it would be 100 plus 10K, so 110K. So 5 divided by our total multiplied by the resistor value here. So in the case of light, 5 divided by 10K multiplied by 1K. That would be our voltage here. And I'll do the calculations in just a minute. In the other way, 5 volts divided by 110K multiplied by 10K. We would have a different voltage there based on our 5 volts. So let's do the calculations. So here are the calculations. RT equals RA plus RB. RA, let's say, is our fixed resistor here, and RB is the value of our LDR. So in the case of light, RT is 11K, 10K plus roughly 1K. In the case of dark, RT equals 10K plus roughly 100K, so 110K. So in the case of light, what voltage we would see here roughly, in the case of a lot of light, it would vary in between levels of light, but in a lot of light we would see 5 volts divided by RT, so 5 volts divided by 11,000 times 1,000, which is our secondary, our RB value, is 0.45 volts. So that's what we would see here, 0.45 volts, roughly, in a very high light situation. Dark. We would take 5 volts, which is our power supply voltage, our VCC, divided by RT, which in the case of darkness would be 10K plus 100K, 110K, times RB, which in this case is 100K because of darkness. And our voltage here would be 4.54 volts. So what I'm actually going to do is I'm going to hook that up. I'm going to use my breadboard, connect a 10K ohm resistor and the LDR, and I'm going to show you the varied voltages based on how much light is hitting the LDR. So just give me a second to set that up. Okay, so I've got my circuit lined up. Resistor, LDR, multimeter right in the middle, measuring right here. In room lighting, there's about 870 millivolts right in the middle. If I put my laser on it, roughly 120 millivolts, and if I put my hand over it, not complete darkness, 2.5 volts. If I turn off the light, it would actually be up to close to 4.5 volts. So what I want to do is I want to create a circuit that the circuit will lay dormant when there is less than 500 millivolts on it, and when there is more than 500 millivolts on it, like right now, 870 millivolts, the alarm will activate. Now I'm going to actually make a whole bunch of different circuits, and this is a block circuit, so you can basically follow along and do a bunch of different things at your end. You can try a bunch of different experiments, because I'm going to be making 3 different videos. So now let's talk about our comparator circuit. We have to design a comparator circuit. So let's do that. This is our comparator circuit. Now if it looks complicated, it's not at all. It really depends on whether or not you've done something like this before. This is a microchip. I'm going to use the LM324. It's actually got 4 comparators here. This is a symbol for comparator. There is a plus sign and a minus sign and an output. In this case, we've got our output connected to a current regulating resistor and an LED for an indicator. And once we actually build the circuit, we're going to stop the video and we're going to build on it in another video. But regardless, what we have to do is this line, our plus input, is connected to our LDR circuit over this way, and the negative is connected to another resistor divider network made up of 2 resistors that are fixed values. Now what we want to do is we want to set a reference to the negative, because how a comparator works is if there's more voltage, a higher voltage at the positive than there is at the negative, the output will be high. If there's a higher voltage at the negative than there is at the positive, the output will be low. So it compares voltages. It's a really wonderful little circuit. So we based on what we just saw, we want to have a circuit that has a reference on the negative of 500 millivolts. So we want to have 500 millivolts right here. So what we have to do is we have to create that. So let's do the math. The math here is pretty easy, actually. Just follow along, it will make sense. We want 500 millivolts here. 500 millivolts, which is 0.5 volts. 500 millivolts equals 0.5 volts. We want to see what percentage that is of our supply voltage, which is 5 volts. So we take 0.5 volts divided by 5 volts, and that gives us an answer of 0.1, which equates to 10%. So between the total resistance of our new RA and RB for the secondary resistor divider, we want our RB to be 10% of the total. So if the total is total can be 10K, it can be 100K, it doesn't matter. Preferably 100K, because that means that there's less power being dissipated in the circuit. The higher resistance, lesser power consumption. So let's say our total between RA and RB, RA plus RB, is 100K. RT equals 100K. So we want to have our RB at 10% of this. So 10% of 100K is 10K, and then that'll leave 90K for RA. So 10K, 90K. Now, 90K resistors aren't exactly easy to come by. There are all sorts of weird values out there, but you know, if you're off by a few kilo ohms, it's really not going to matter all that much. Just get as close as you can, and if you have to use, you know, 2 resistors in series here just to make around 90 ohms, you can do, or 90 kilo ohms, you can do that. Really not all that difficult. 91K is a standard value, so you could use a 91K here. Anyway, that's going to give us a fixed value of about 500 millivolts. So I'm actually going to build this resistor divider as close as I can. I'm going to use a 91K and a 10K, and we're going to see how close I am to 500 millivolts. So 91K connected to 5 volts, and the secondary to a fixed 10K, which is our RB, right here to ground. So right in the middle, I'm going to measure at the same spot, just like we did for our LDR divider, and I'm going to power it up. 481 millivolts, close enough. And you can try that at your end too. You can use those same formulas to make your own voltage dividers very easily. So now we have to use our comparator circuit. And I've already really shown you the schematic, but before we go on, I'm going to do a quick introduction on the LM324 quad op amp. The LM324 is a 14-pin chip. I'm going to be using a DIP package. By package, I mean just the package of the actual IC. There's surface mount. This is obviously through hole for breadboarding, and you can find this at any Radio Shack. It shouldn't cost you more than $1. On the left side of the chip, there's a notch. As you see on the schematic here, there is a notch as well on the left-hand side. That's your reference. Now, each of these chips needs a voltage source. In this case, 5 volts and ground. As you can see, pin 11 is ground. And you can actually Google LM324 pinout and go to Google Images, and you'll find this exact image. And you can see the data sheet too. Your V plus is right here. It's pin 4, so the 4th pin from the left on the bottom. So we want to connect 5 volts here to power the chip. We want to ground our device, or ground our chip, so connect pin 11 to our ground line. And as you can see, there's 4 op amps here. We only need one of them. So we're going to use the one in the lower left-hand corner, pins 1, 2, and 3. Pin 1 is the output, pin 2 is the negative input, and pin 3 is the positive input. So let's put our chip, our LM324, on our breadboard, and we can connect up our circuit. So again, one of our op amps, pin 3, positive input, connected to our LDR voltage divider. Pin 2 connected to our fixed voltage divider, which should have around 500 millivolts on it. Connect to pin 2. Pin 1 is our output, which we will talk about in just a minute. We'll put a 470 ohm resistor. It really doesn't matter. 390 to 1000 should really light up an LED, so 390 to 1K should be fine. LED, if you don't know anything about LEDs, the long lead is the positive, which is connected to the resistor. Short lead is your negative, which is connected to the ground line. But I'll show you that in a minute. Pin 4 of the op amp, connected to 5 volts. Pin 11 to ground, just like we talked about. So if you actually look up here, what I've done is I have connected pin 11 to ground and pin 4 to my 5 volt line. Now I'm just going to take some random wires here. As per the schematic, as I mentioned, pin 3, which is right here, will go to our first voltage divider, our LDR divider. And pin 2 we'll go to our fixed divider of 500 millivolts. Very easy to do. Now, you don't need to use big bulky wires like this. I'm obviously just doing this as a quick tutorial. You can make yours a heck of a lot neater. Or you can solder it onto a proto board. So anyway, we're pretty much ready to test it. I've got my laser pointed at my LDR fixed right there. And there's my LED. It's actually pretty sensitive, not overly sensitive, not the most sensitive circuit in the world. I've created really sensitive ones, but that's because the response to the LDR isn't fantastic. But it certainly is reliable. So, based on what we did in this, if you paid close attention, again, I'm sorry if I'm a bit of a rambler. I just hope that you got enough. It's basic, it's basic arithmetic to design some of these simple circuits. And what I'm going to do in the next two videos is I'm going to show you what you can use that outputted signal from our comparator. We can use that for a bunch of different things, and I'm going to show you, and I'll leave it as a surprise. So if you're interested, please come back to my channel, subscribe, like it if you enjoyed it, and let me know if you enjoyed this tutorial. Based on the responses, I'll just continue making them whenever I have time. And again, this will be the three-parter. This will be an electronic bricks. So we're going to be piece by piece by piece. We'll add to it. So thanks for watching, and have a great day, everybody.